Okay, so in the last class we had started alright. So, in the last class we had started discussing different cost function, still convex, but has different properties than a circular one. Okay. Now, one question, are these contours discrete or they are continuous in nature? They are continuous in nature, right. No matter where you are, you will always be able to find a, in this case ellipse, and in that case a circle. Okay. Always be able to find a circle. So see, whenever I draw, whenever I draw something like I go from here to here, it's not a discrete level. It's just that because I have drawn these circles, otherwise this could have gone anywhere. Okay. There is no limit on that as such. Okay. So, now talking about this, let us keep it here only. Yeah. Now talking about this, right? How do we handle this situation? What is the problem in this case? If you are talking about this point, then your minima is here, and the line and the vector joining, I mean the line, the vector joining, this point to minima is somewhere very far off from the gradient that you are getting, right. So, they are not the same thing. My gradient is taking, my negative of gradient is taking me in this direction, whereas this is the line that takes me to the minima. How do we take care of this problem now? Updating gradient as well. How do we do that? I mean, see, these are the problems of gradient descent. Why? Because remember, we had written Taylor series, f of x plus delta x can be written as f of x plus delta x transpose grad f plus delta x transpose Hessian of f, and then again x, and so on. This can just keep on going, right. So, in this case we have said these terms, they go to these terms, and the later they go to 0, only this remains. If Hessian were here, Hessian would be able to tell us, would be able to guide us in this direction, but Hessian is not there. Okay. So, these are, so now we start seeing the cases where gradient alone is not sufficient, you need higher order terms. So, cancelling them was a bad idea, but it is still a good idea. Why? Because you will have billions of parameters here, you won't be able to handle that Hessian anyway. Okay. So, we don't, I mean, even if this were good, we won't really want that. Next. So, how do we start doing here now? We had started talking about, so my grad J is 50W 2B. How will my update look like? WB equal to WB minus alpha times, which is 50W 2B. Okay. Now, are these W's and this W same? I mean, think over it. I am just writing in terms of symbols. Okay. So now I am here, negative gradient is going to take me in this direction. What do I do? Yes. What will happen in this case? See, I am here, I am going in this direction. What happens if I am here? What happens if I am here? In that case, what will happen? Right now, I had a little bit more component towards the minima. Now, if you are here, this is your gradient and this is the negative of gradient. You are further off from the minima in some sense, right? How do we take care of this problem? What will happen in this case? So now I start from here, okay? And how do we, or maybe I start from here only, okay, this point. How do I proceed? I take gradient, negative of gradient, so I am here right now, I do all this computation. Where will I be updated? On this line somewhere. So let's say I end up coming somewhere. If I overshoot this guy, then what should I do? Reduce the alpha, okay? But assuming alpha is well chosen, so let's say I end up here. So from here I end up being here. Now what happens? I will do the update here. Tell me, where will I go from here? So here, what is gradient? This one. Negative of gradient will be exactly opposite of this. So I go from here to, let's say, somewhere here. Does there exist a concentric circle there too? It does. Okay. Now what happens? What do I do now? Take gradients here. So I actually come back, let's say here. So what kind of trajectory I am doing? I am actually going towards minima, but something like that. Okay. How do we solve this? What are the problems with this kind of gradient updates? Yes. So let me quickly repeat for those who are late. We have update equation of this kind. Okay. This is my gradient. This is my gradient. Negative of gradient is this. I take a step on this line, reach here. I take a step on this line, reach here, and I keep on doing this, right? So instead of going directly to minima, I am taking this zigzag path to minima. And question is, how do you solve this problem? Huh? So one idea is you take small steps. So then you have to help me out this side. I start from here and I want to take small steps. So I keep alpha very low. Okay. If I keep alpha very low, let's say I reach here. What do I do now? So gradient will be here and here. So very small steps and maybe you will finally reach here. What is the difference between this way and this way? Exactly. इधर देखो. नहीं तो बाहर. Yes. So what is the difference between these two? Give me the number of iterations in both the cases. They are the same. So my learning basically same, right? It is still taking me the same number of iterations. So if I were taking 10 iterations to reach from here to here, I am taking roughly 10 iterations in this way as well. So just slowing down does not help. My learning is actually slow in both the cases, right? Learning is slow in both the cases. How do I speed up it now? And so this is what we mean when we say learning is slow. What does it mean? You have to update your gradients, you have to update your weights for very long to reach to minima. Okay? Issue is okay with everyone? If I take a reasonable alpha, the problem is I'll end up doing zigzag. If I take a small alpha, I will not be doing that much zigzag, but I am going to take the same number of updates, same number of iterations anyway. So how do I improve on this? So if you start from here, you take this alpha, then you take smaller one, then you take smaller one, doesn't really help you much. So what you can do? I mean, I think you can still answer this. Use vector sums. We did this in AI as well. Exact same thing we did. Resultant, right. So how will resultant help me? Right, just a second. So remember we did something of this sort in AI as well when we were taking exponentially weighted averages. So what are exponentially weighted averages? What are exponentially weighted averages? So let's say what I do is I take a gradient. So I do something like this. What is this? We have talked about this kind of equation before. So VDW equal to VDW previous one plus 1 minus beta times the current one. So let's say if beta is something like, so sorry, there will be a beta here as well, right? So if I take beta to be 1, what will happen? If beta is 1, then this current is 0 and I take only the previous ones. If beta is 0, then basically I go to my current gradient descent, whatever I am doing right now. Okay. So beta is 0 takes me to the current regime that I am doing right now. Beta equal to 1 just ignores the current one. We don't want that one either. Beta should be somewhere in between, right? Usually beta is 0.9, let's say. So if you choose now whatever beta is, what is this equation telling me? By current, so what are the dimensions of this guy? Can you help me decode this equation? Who is scalar, who is vector, what are the lengths? Beta is a scalar. So beta is a scalar, that means these coefficients are scalar, I am done with them. What about dw? dw, just take example from this one. What about dw? What is dw first of all? dw is just nothing but gradients. So basically grad j that we were talking about. Okay. So what are the dimensions of dw? This is nothing but 2 cross 1. Number of parameters, hash parameters cross 1. This is scalar, done. What about VDW? What should VDW be? What should VDW be? 2 cross 1. Why 2 cross 1? It must be a vector because this summation has to make sense. So for this summation to make sense, it has to be 2 cross 1, but there are reasons other than this as well. What is VDW? VDW is just in some sense vector sum of all the gradients until now. It is a sum of all the gradients until now. It will have the same dimensions as the gradients. So 2 cross 1. What about this guy? Same thing. This is 2 cross 1 or hash parameters cross 1. Okay. They are all gradients, so they will have the dimensions of gradients. So is this equation fine? Alright. Now, and similarly, because we are always treating B differently, you can similarly write for VDB equal to beta times VDB plus 1 minus beta times VDB and so on. By the way, else interpretation is same, right? Huh. See, I am doing two things here. One, I am taking an example in which there is only one W and one B because we can't really visualize something beyond that. Okay. Whereas, so for what we are doing right now, this W is 2 cross 1. But in general, the way we write in algorithms, we treat B separately and W separately. Okay. Else equation wise they are the same. Because you have different W's matrices, different B weights, right? So they will be different. Right. Now you have to help me out in finding the solutions to this problem that we have had. How does this help me get rid of this zigzag? Yes. So these are the equations, but these are, what are these equations doing? So just quickly tell me what will be the impact of these equations here. Let's say if I am here, what will happen? Directly minima. You are here, so let's say if you are here and you have history of these 4 vectors, what will happen? See, which directions will cancel out a lot? Which direction? In the W direction we had higher derivatives. What will taking vector sum, see this is a vector sum because in the end you are taking sum of these vectors, so it is a vector sum. What will happen? What will happen if you add these vectors, these 4 vectors, 1, 2, 3, 4, what is their vector sum? You start from here 1, 2, 3, 4, what is the vector sum? I have this vector, what is their vector sum? I move this here, right, and then this is their vector sum. This vector, they are all already aligned. What will be the vector sum? This thing, a vector joining from this point to this point. So this is the sum of your, so this is roughly your VDW. Why I said roughly your VDW and not exactly VDW? Because you are not summing them directly. You are having coefficients called beta, and so if you are here, and you came from here, of these four vectors, of these four gradients, which one will contribute to the most in this case now, wherever I am? Which one will contribute the most? The latest one or the previous ones? Latest ones, right? And previous ones will be contributing less and less. Why will they be contributing less and less? We had done the exact same thing in AI. So let us write this now. So let's say we are writing for, so let's say VDW4 I am computing. VDW4 will be written as this equation. VDW4 will be written as beta times VDW okay, plus 1 minus beta times DW4, let me call it this way. Okay, I mean, I might be doing something wrong with these things, or let me not do it. Let me just call them V4 will be beta times V3 plus 1 minus beta times DW, let's say. Okay. Now, I want to write V4 in terms of V2. How will I do that? V4 equal to beta times, what is V3? Beta times V2 plus 1 minus beta times the previous one. So let me call DW4, this is DW3 plus 1 minus beta times DW4. How will I write V2 in terms of V1? So see, when you look at V4, it is a function of beta square V2. So if you compute V10 will have beta to the power 8 or 9, and then V2 will be coming there. What does this mean? Contribution of V2 will be less. I mean, so this V2 is still a vector sum. Let me write this V4 in terms of beta times V1 and so on. So the last one will have a coefficient of beta to the power 4. Next one will have a coefficient of beta cube and so on. Okay. So those that are further away in time, they are contributing less. Those who are the current ones, they are contributing the more. And why is this the right behavior? Why do we want this? See, you might have done whatever here, but I care more about what is happening currently. So we give more weightage to what is happening currently, and that's why I said the vector that we are talking about, it is not this vector. Okay. It is not this vector, but it is something which is more in the direction of B and less in the direction of W. How many of you are not okay with this? Raise your hands. I can assure at least 75% are not okay with it.
Like direction
Which direction? No. So let's flush everything. Let's start from the fresh. I wanted to go from here to here directly, but I couldn't because I am using gradient descent and gradient is taking me in the negative directions of gradient. In this kind of landscape, gradients are actually very far from minima. So I take this zigzag path. In direction W where the coefficient is high, right, I do a lot of zigzag. Where coefficient of B is small, I take smaller direction, I take smaller steps into that direction. Okay. So we don't want this kind of zigzag. And why we don't want this kind of zigzag? What is wrong with this? Slow learning. You will have to run for more iterations. If you are trying to train things like GPT, which take months to train, then basically you are talking about, additional months of compute, additional months of dollars, additional months of time and so on, everything. So you want to reduce this. Ideally I would want if I could directly reach from here to here or from here to here, but it turns out it is not possible because you are dropping higher order terms. Hessian would have given you that this curvature is such that gradient line search will not take you there. So make use of Hessian. But if you are training GPT, you have GPT-3, you have 175 billion parameters, you don't want to take Hessian there, no matter what. So then what do? Then how do you solve this? I have already answered everything. So this is the problem, how do you solve it? I can randomly ask anyone. Yes. How many of you want me to repeat this? This zigzag is fine? So if this zigzag is fine, what we are saying is we just take sum of previous ones. We take contributions from previous ones as well. Now this has two effects. One is what? See, how does this valley look like? Just a second, देखो. Okay, so equation is 25. So let me just write x square plus y square and I need to do one more thing. Just a second. Okay, so let us not do that. What will I rather do is, I will equal to 4, let's say, this one. This is x, this is y. Okay, so let me, for our visualization, let me flip these guys. Right, this one. Now, if I repeat the same thing, इतनी देर में तो लिख दिया होता है यार. हाँ, नहीं, आई थिंक आई विल राइट. अब जाके हुआ है वो. Okay, so let me just take it 10 and this one, let's say 25. Okay, okay. क्या बोले? हाँ, जरूरत नहीं है ना अपने को. So what is this right hand thing? These are the contours, right? So these are the possible values of j for us. So we are not looking at how the function looks like, we are looking for WB plane and how do contours look like. So how will my function look like? It touches here and then a compressed ball kind of shape, and as you go outer, your thing is higher and higher, the value of the function is higher and higher. Now in this case, अब मैं यहाँ पे क्यों लाया था भाई? नहीं, विजुलाइज तो सब चल रहा था यहाँ पे. हाँ, ये सब तो हो चुका है यार. But anyway, it's good to visualize. लास्ट क्वेश्चन क्या पूछा था मैंने, ये बताओ. चलो होपफुली याद आ जाएगा इसी क्लास में. कौन सा? नहीं, दिस इज डिफरेंट फ्रॉम प्रीवियस डीप लर्निंग. अच्छा, अब ठीक है, जो हो गया वो हो गया. अब देखते हैं. So दिमाग हटेगा नहीं वहां से यार. ठीक है, क्या बोल रहे हो? So, all right, enough. Come back here. So, हाँ? नहीं, अभी नहीं. हाँ? यार, resultant we had talked about. सिर्फ वापिस ही बता रहा था क्या? हाँ, so then all you do is, you know, just see, there is one thing that we can show through this figure and which was not so trivial from there. If you see here, these parts, I mean, I have not really been able to do these kind of ellipses, because in the end वो थोड़ा circular बन ही जाता है. If you see these kind of points, right, here gradient will be perpendicular to this. So a perpendicular, so you are still in WB plane, you are not on a hill, you will move in this direction, and this direction when you compute the value of the function, right, you get those values which are increased maximally. Why? Because gradient is the direction that gives you the increase, the maximal increase in the function. Any other direction that you will take from this point and you walk the same distance, right, the value of j will not increase as much as it will increase in case of the direction of the gradient. Okay. So if you start from here, you will take much. Okay, yes, the point was, I was about to say that in this case if you see, since ellipses are more circular, right, we have reached from here to here in maybe 5-10 steps. But in reality, if you see, if you start from here, right, it will be a much longer journey to this particular point. And if instead of 25, right, let's say I make it 250 for the time being. भाई कर दे 0 यार. अरे वो 2500 कर देगा यार. चल. So this one, right, and if I make a 0 here, so you see these, no, anyway, the more the coefficient, the worse are these guys, and if you end up stucking in such a region, what will happen? So learning will become very slow. Why? If I am here, I take a high learning rate, where will I end up? I'll end up somewhere here. And what's wrong with somewhere here? That's very far off. My value of j has increased a lot, significantly, right? So I should not go beyond this black concentric circle. And to ensure that, what am I supposed to do? Learning rate is small, but how will momentum help me? I mean, how will those gradients help me? The summation of gradients. So they dampen the oscillations and they guide me more towards this. So it works much better than the vanilla gradient descent. Is this a perfect solution? Not really, right? But works much better than gradient descent, vanilla gradient descent, and does not require anything like Hessian. Okay. Exactly. What is the question? Right? This VDW is guiding you more in this direction and not so much in this direction. So it will take input from this guy as well. So your final thing will be a vector sum of beta times this vector, which is guiding you more towards the minima, and 1 minus beta times dw, which is my current gradient. So their resultant will be better than just this one direction. I can see people sleeping, people are with their cell phones. Yes, questions? These full steps? No. देखो, ये तो because I am showing you this figure, it looks like you are doing full, right? But think of it this way: one, I take this step; second, I take this step; third and fourth. Okay. Now assume I have done these 4 steps. Let's start talking about this one, and also assume that I am just taking a vector sum of previous ones, so not beta times 1 minus beta times, right? So if it is a vector sum, I have this guy. Now this one plus this one, because this is my new one. So if you see this particular step, the 5th one, original is taking me in this direction, but resultant is taking me in this direction. I have more component in B direction compared to earlier. I have lesser component in W direction compared to earlier. So I have tilted my vector towards the right direction. Okay. And these are still very nice kind of valleys, but anyway, now we right. So we know how to do this, so we just write down the equation. So we write down the gradient descent again, and then we'll take a break. So help me write down gradient descent again. Yes. For epoch, let's say 1 to 100, there is nothing special about this 100, I just have to write a number, I wrote it. What next? Compute J, and I am still doing batch. So compute J, compute grad J, update W equal to W minus alpha grad J, B equal to B minus alpha, but this is the old one. How do I write the new one? Where should I make changes to incorporate momentum? Sorry? Yes. Should I make any changes here because of the momentum? Should I make any changes here? J will still be computed the way it was being computed. Grad J? Grad J, because they are gradients on a point. So again, my update has changed. So how do I update now? So we have W equal to right, and how are you computing this VDW? VDW is beta times VDW plus 1 minus beta times DW, and VDB will be beta times एक सेकेंड प्लस 1 माइनस बीटा टाइम्स dV. हाँ, all these updates we have been writing W equal to W minus alpha grad J. तब क्यों नहीं बोला? All right. So this is gradient descent with momentum. The name of this algorithm is gradient descent with momentum. हाँ, इससे बेटर क्या होगा भाई? चलो डन, ब्रेक.